All right. Hello, everyone, and welcome to CU Prime's first annual physics debate. So my name is Tyler McMacken. I'm a current PhD candidate in the physics department here, and I'm representing CU Prime, which is a student organization who is designed to do a bunch of things. So CU Prime is completely student-led, and its mission is to foster an inclusive, open environment in the physics department at CU and beyond. And the way that we do that is through a number of different programs. We have a mentorship program that runs year-round between graduate students and undergraduates. We hold a class that's run by students each fall semester, in which students get the opportunity to engage in science in the real world and learn some things that you won't learn in traditional content-based classes. And we also host a talk series of bi-weekly talks, usually given by graduate students every other week, where they talk about their research in a way that is accessible to anyone. And as part of that talk series, every once in a while, we have special talks. So usually in the fall semester, around the time the Nobel Prize comes out, we'll have a talk related to that. And some new thing that we're starting right now is to have a debate each spring semester. And so the idea is to have two faculty members hash it out. And that is what we're here to do today. So the format of the event that we have before us today is going to be in three parts. So first of all, each of our two debaters will be given some time to give their opening statements. And they'll be given 8 minutes each. That timing will be strict, so make sure you don't go over. And we will also have a panel discussion after that time, in which Professor Noah Finkelstein will be moderating and asking questions to both the debaters. And following that, we'll have an extended time of audience question and answers. And so if you guys have questions for the debaters, that will be the time to do so. Now, in order to decide who wins the debate, I should mention that this is a debate, and usually in a debate there's a winner and there's a loser, because, I do not. Right, and so we are not quite going to follow the traditional philosophy debate or law debate style format, in that usually if we want to settle a matter in science, we do so, there's a set way of doing that. You propose a model, you run an experiment, you interpret that experiment, and then you publish your results, or you go to a conference. The way that you typically do not settle a matter and come to scientific truth is by having a debate. But we would like to do so because it's fun, and hopefully we all learned something here today. And also there's a lot of problems coming with interpreting experiments, and so there's plenty to discuss and learn across the board. And so what you have behind me is a QR code. There's also a link below that if you just want to type that in. And this is an audience survey. So there are two of the same question that essentially ask the question of tonight's debate. So I would ask that you all fill out half of that survey now, the first question, to get a baseline. And then at the end of the survey, we'll ask you to fill out this second question so that we can see how many people's minds changed. And with that, we'll then have a winner and a loser. We have prizes for the winner of tonight's debate. I don't know if, do we have, let's see, I'm trying to see where the prizes went. They're somewhere. I'll just say what they are. So the winner of tonight's debate is going to receive 10 quantum coins. And what that means, this is a cryptocurrency. And there's a cryptocurrency called QTUM, or quantum. And they will be the proud owner of digital currency. We also decided to give a consolation prize for the loser. And so because they obviously need to do some more studying, we'll have a book called Quantum Information for Babies. All right, so in order to decide who goes first in this debate, we decided we could just flip a coin, but because we're talking about quantum measurement today, why not flip a qubit? And so we did that, and because we're at one of the world's leading institutes for atomic, molecular, and optical physics, we went over to Adam Kaufman's lab, and the graduate student Aaron Young was very kind enough to do an experiment for us to decide who goes first. So the way that this works, we have an array of atoms. These are strontium atoms, and they're prepared in a superposition of quantum states where the electrons can either be in the s orbital or the p orbital. And then after some time, they pulsed it with a laser at just the right amount of time so that it would flip and collapse into either the s orbital or the p orbital. So if it stayed in the ground state, the s orbital, then those atoms, they drop them out, and you'll see those as just black gaps in the next picture. But if they went into the excited state, then we call that heads up, heads, and the atoms will stick around. And then I'm skipping out some details, but essentially, Professor Graeme Smith called heads. And so if you see, we pre-selected a specific atom, and we said, what state will this be in after we perform this operation? If it is still around once we do it, then we call that heads. And there you go. We did our quantum measurement. So Professor Graeme is going to be the first to go. Right, wonderful. So let me introduce our two speakers briefly, and then we will get on with the subject of today. So first of all, we have Professor Chris Fuchs. He is a professor of physics in the College of Science and Mathematics at the University of Massachusetts, Boston. He started out his career as an undergraduate at the University of Texas at Austin, studying under John Archibald Wheeler. And since then, he has moved on to work at Bell Laboratories, Raytheon, the Perimeter Institute in Waterloo, the Max Planck Institute for Quantum Optics in Garching, Germany. And he's also the author of the book Coming of Age with Quantum Information, and is the pioneer and world's leading expert on the field of QBism, which we are going to hear a lot about tonight. With that, he was elected as Fellow of the American Physical Society in 2012, and there are a plethora of other awards and fellowships that I don't have time to mention. One other fact that I'll give is that his most recent paper that he's published is titled Quantum Mechanics. It's all fun and games until someone loses an I, the letter I. Yeah. All right, so Professor Chris Fuchs is going to be joined by Professor Graeme Smith. He is a professor of physics in the College of Arts and Sciences here at the University of Colorado Boulder, and he also holds current positions as a Gilla Fellow and as a director of the Center of Theory of Quantum Matter. He earned his PhD in physics in 2006 at Caltech under the advisement of John Preskill. And since then, he's worked at the University of Bristol. He worked at IBM, where he became a Kavli Fellow, and here at Boulder, where he earned an NSF Career Award in 2017. And starting this July, he's going to be moving to the Institute for Quantum Computing in Waterloo. So Graeme has a thriving Twitter account with over 7K followers, where he rocks the world, the world of quantum Twitter. And among his most recent papers, published the same weeks as Chris's, is one titled The Platypus of the Quantum Channel Zoo. So those are our two speakers, and to introduce the topic of tonight's debate, I'm going to call for Professor Noah Finkelstein, who is in the Physics Education Research Department here at CU.
Thank you so much. It is such a pleasure to be here, and I want to give a huge shout out to Tyler and Jacob and all the CU primers here for making this happen. Thank you both and the whole crew so much. I'm a huge fan of this department. I'm a huge fan of you all for being here. Thank you so much for joining and taking the time to be here. And hopefully, oh, there we go. As mentioned, I'm Noah Finkelstein. I'm very grateful to be a professor here in this department, to have worked with many of you all so far. And I also want to give a shout out to the departmental sponsor for the CU Prime program, for so many programs, the undergraduate and graduate initiatives that we engage in, enabling our student groups to do the work that they're doing, which is the Department of Physics, led by Professor Mike Ritzwaller. Thank you for your support, Michael Ritzwaller. Okay, So we could spend the entire time talking about what is quantum, and it's a subject of lively discussion and debate. And you all might think that you know what it is, but I bet you have something else to learn here on that in this enterprise. And I won't belabor this point because I'm supposed to get out of the way and let two theorists debate something that is fundamentally experimental. Hey. So I just want to point out and give some foundational principles. And these are slides, actually, that were assembled by Phil McCoten, who's an alum from our department in the AMO program and current head of executive director of our Qubit initiative. Please get involved in that. Please join, if you haven't heard about it and you're an undergraduate, please consider joining the Quantum Scholars Program in the future. And shout out to those quantum scholars who are currently here. So you can sort of, in some regards, people break the quantum mechanics into two sort of revolutions, one early on and then continues to the present. We'll call that quantum 1.0 and a current regime of quantum 2.0 that we're really capitalizing on. But there's some fundamental characteristics here in the quantum 1.0 world. One is that unlike the world that we live in a day-to-day basis, our systems are fundamentally discretized, and we can talk about discrete energy levels. And why does that matter? Because that gives us applications to all kinds of important things like communication, like one plane communicating to another plane, I don't like you so much, with a high-power laser, anyway, all kinds of remote sensing and whatnot, and also a fundamental shift in our understanding of quantum systems here, that we are moving from a deterministic world to a probabilistic world, instead of understanding exactly where a particle is going to be, when it's going to be there, and being able to put well, we can crash, for example, a rover into Mars because we got our MK units mixed up with CGS units, I think, or maybe it was the British version of that. In a sort of completely deterministic way, we move into a probabilistic realm and we think about things differently. And that has all kinds of implications. It's changed our view about it. Actually explains what I consider all of chemistry here, and our understanding about the nature of atoms and bonding and the rest of it. And I mean, just down the road here, we can have truly random number generators. And there have been huge impacts of this in terms of our economy, technology, quality of life, and indeed national security here, a whole array. But we're on the verge now, we're in the midst of another revolution here, and there are additional characteristics here that I just want to unpack for you very briefly, which is to say, fundamentally now we're actually taking advantage of the fact that we think of systems in the quantum level as waves, and hence they have interference patterns. And you might say, yes, so what? But I swear, I just heard our own Professor Dana Anderson give a talk 2 days ago that was the equivalent of flying carpets, near as I could tell, for those of you who joined. And we see all the time, you can get two atoms or bunches of atoms to interfere with each other with our Bose-Einstein condensates. And that just is mind-boggling to me. But maybe you understand that. Maybe you also understand the nature of superposition, that we consider the states of systems to be superposed. A coin is both heads and tails until we measure it in that system. And similarly, that two systems are entangled. And I'll unpack that just a little bit in a moment here for you all who may not have thought about what entanglement means, but this is what Einstein so disagreed with and referred to as spooky action at a distance, that I can have two systems that are coupled with each other at very remote places, and my engaging with one determines and impacts the outcomes of the other far faster than the speed of light. This has huge implications. We are world leaders in quantum sensing and measurement, quantum computing and simulation and quantum networks. These are different areas that we are advancing right now. So just, I mean, for those of you, I mean, how many of you here are super comfortable with quantum entanglement? Okay, thank you. Although I'm a little surprised by some of my colleagues not raising your hands, but maybe you're right. You shouldn't be comfortable with that. This is the world that we live in. And could I just get a quick volunteer here from the audience to engage a little game show here to follow? Just a quick volunteer. Thank you. What's your name? Marcos. All right, everybody, thank Marcos here for joining us. All right. In our world, we understand that I can take a red sock and a blue sock, right? And I want you to follow this, because are you from New York by any chance? You got a little, no? Okay, too bad, because New York street corner. So what we're going to do, we're going to put them each in a box here for you. We're going to cover them. Which one is the red sock and which one's the blue sock?
Right is red.
Right is red. You are right as rain. Awesome. Thank you, Marcos. Move it. All right. Okay, so now, just follow these, Marcos. All right, and I'm going to separate them, I don't know, on opposite sides of our galaxy here. All right? Can you tell me definitively which one of these is the red sock?
Yeah, the right is red.
The right is absolutely red. Okay, are you a physics major?
Biophysics.
Biophysics, okay, congratulations. All right, would you bet your major on this?
Let's do it.
Marcos, I'm not sure. I'm not offering this bet, nor am I actually authorized, perhaps by whoever's funding your education, to do this. But sure enough, if I open this right box, what's the other box? It's blue, right? All right? Pretty smart. All right, go biophysics. No question about it. This is red and this is blue. The question is, in our world, was this box over here red and blue the entire time? Red the entire time, the box on the right? Yes. In our macroscopic world, it is blue. It is red the entire time, or at least that's the way we think about it. Although some people don't ask those questions, and we'll get into this. But we referred, in the quantum world, one could imagine these socks as entangled. And only when I measure this red sock does the other sock become blue. This is the world of entanglement. Right? That this box on the right contains a half red and half blue sock. It is in a superposed state. But the act of measurement collapses the wave function of this system to become red, right? And this is, not only is this a question of philosophy and great import to theorists, but it has huge pragmatic applications in our world. Huge applications, whether pharmaceutical or climate, medical, navigation systems, and all the rest of it. Or what I actually challenge you all is for you to decide what it is that we can do, because we are on the verge of figuring out new ways for living and engaging in the world. So I'm really grateful to introduce two people who are going to help us unpack whether this is a red sock or a blue sock and when that happens here. And so we're going to turn this over now to our two luminaries here, each with 8 minutes of opening remarks. Answering the questions or the charge, considering in various implementations of quantum mechanics what physically happens to a wave function when a quantum state is measured. They will each have opening remarks. They will then engage in some structured debate around questions, and then you all will be charged with finishing this up and challenging them in particular ways, and then ultimately decide, do we have a winner and a loser? Do we have a winner and a winner? A loser and a loser? A half winner loser. All right, you decide. All right, so with that, let me turn it over, and please join me in welcoming Professor Graeme Smith. Who has the hometown advantage?
Yes.
Do you want a computer?
Oh, yes, my computer. I will plug it right in. Okay. We're going to do this like this, okay? You're going to be able to see...
I'm just saying an experimentalist would have had the right view up there.
Well, I appreciate the opportunity to speak to you, and my goal today is really to demystify and slightly... let's my goal is to make sure you shouldn't be afraid to embrace many worlds. Okay? Because many worlds is a bad name. It's really the most conservative and I think natural interpretation of quantum mechanics. But first I want to talk about what is quantum mechanics. So here's very simple description of what quantum mechanics is. There are states. Yeah, we usually choose them. You talk about Hilbert space if you're doing fancy quantum mechanics. They're just little complex unit vectors that point in some direction. And you can do measurements, they say. The way you do it is you pick a basis or an operator you're going to measure. And given, I really should have taken you up on the pointer, but I didn't. Oh, thank you. Given some state, psi, which has amplitudes alpha and beta, if I decide to measure the 0, 1 basis, I get either a 0 or a 1, some definite outcome. And that's what I teach. I've taught in this room before. You get a definite outcome, either 0 or 1. The probability is the amplitude squared. That's what happens when you're doing a measurement. Okay? But when you're not doing a measurement, there's something else that happens. The Schrodinger equation says, it's a fancy differential equation, but basically what it says is you take your state and you rotate it. Yeah? So for qubits, it's very simple. You just apply some unitary matrix. That's just something that doesn't change the length of your vector. And it just rotates your vector in some direction. So there is tension between these two axioms of quantum mechanics because on the one hand, the Schrodinger equation says what happens when a system evolves is that it rotates and doesn't change its length. And that's a very continuous process. It's described by a differential equation. So if you wait just a tiny amount of time, it just sort of rotates just a tiny bit. On the other hand, you've got this measurement thing that happens, which is that all of a sudden, once you've decided to measure something, there's a discontinuous update of what your state is. And it either becomes the 0 or the 1 state. And the tension there is that I should be able to use physics, and specifically the Schrodinger equation, to describe the process of measurement. And if I do that, then the process of measurement should not involve any big jumps in the state of the system. It should instead evolve just according to the Schrodinger equation gradually. Whereas if I take seriously this measurement postulate, it says there's going to be a quick update as soon as you do the measurement. Okay, so that's the tension between these two things that quantum mechanics says about how things evolve. And that generally is referred to as the measurement problem. What are measurements anyway, right? That's what it is. And many worlds is the very, I think, natural decision to take the Schrodinger equation seriously. Schrodinger equation just says there's a Hamiltonian. It tells you the energy of the system. And based on that Hamiltonian, you can derive what the evolution of your system is. So the solution to the measurement problem, as far as many worlds is concerned, is just to say, what measurements? We're throwing out the measurement postulate and we're just taking evolution. Unitary evolution of our wave function. Okay, I'm skipping this. Let's think about how this would work. This is Adam Kaufman, our friend, and I forgot that actually what happens in the lab is the graduate student does the measurement. But I took this picture of Adam, okay? So here's Adam. He's prepared his atoms, and they're in a superposition of 0 and 1, up and down, heads and tails. And the way that the measurement postulate says we should imagine what happens is Adam is going to interact with those atoms in some way. And then he's going to get some outcome, a definite outcome. It's either a 0 or a 1. 50-50 shot at being 0, 50-50 shot at being 1. In this case, it was 0, which corresponds to heads, and then I got to talk. That's nice. But I want to think about this process of Adam interacting with his atoms. And I don't want to use the word measurement to describe it anymore. I want to use the word interaction. Adam has some Hamiltonian, so do his atoms. There's some interaction between them that I can describe according to a Hamiltonian. Schrodinger's equation suggests that when atom and the atoms interact, well, that's not what Schrodinger's equation says. So let's think about me doing an experiment, yeah? And that's my Twitter profile picture. @QuantumGraeme, @Quantum_Graeme. That's what you gotta follow. Okay, so what I say is Adam's in there. He's messing around with his atoms. He definitely interacted with them. But what happened is he's, with the atoms in a superposition of, half the amplitude is in 0 and half the amplitude is in 1. Great. Because, just like Adam had an opinion about what his atoms were doing, I have an opinion about what Adam and his atom are doing. Okay? And then I go and talk or interact with Adam. Yeah? And only then do I say, well, gee. Yeah, Adam, you're right. It feels like a 0. He says, yeah, it definitely is 0. Now I say, wait a minute. That's not what the Schrodinger equation said should be happening. Oops. What the Schrodinger equation says should be happening is that because of the interaction, this interaction is like we talked. Yeah? And because of that interaction, we got into a superposition of half the time we're all agreeing it's all 0, the other half the time we're all agreeing it's all 1. So why did it feel like it was just a 0 when I talked to Adam? Well, this is an experiment you can do. And indeed, we did the experiment back here. So we know for sure, if we take the Schrodinger equation seriously, if Adam interacts with an atom that's in this state, appropriately, instead of collapsing the wave function, he's going to prepare this state. I could just integrate the Schrodinger equation and find this state. The other thing we know is that when you talk to Adam afterwards, he says it's a 0. He doesn't say I was in a superposition. So this is experimental proof that when we are in superpositions, the way it feels to us is there's some definite thing that happened even though we're in a superposition. That's hard to swallow. But it's the only thing you have to swallow if you want to make quantum mechanics consistent and happy in a way that is the timer has. Well, okay, so the experimental fact is that when Adam was in a superposition, he nevertheless reported that during that superposition he was in one thing or the other. And there's a sort of poetic way you can describe this. You can describe this as Adam is always in this state, but this is one case where he says, oh, I'm definitely in 0, and this is the other case where he says, oh, I'm definitely in 1. And the matter of why it feels to Adam like he's in a definite state rather than in a superposition of states is not really so much a question of physics, so much as first of all, experimentally we resolved it. We prepared Adam and his atom in a superposition. And then we asked him what it felt like. And it felt like one thing happened, but not the other. The poetic thing to say in many worlds is that when you feel like there's a definite outcome, there's some other you out there that feels like you have the opposite definite outcome. And that's kind of the only difficulty you have to absorb in order to have a consistent way of talking about measurement in the interpretation of many worlds. Okay, so the moral of the story. We can always describe measurements as unitary interactions between an observer and a system, and it leads to entanglement between them. What does it feel like to be entangled with a system? Well, empirically, it feels like something definite happened, and what selects which of those definite things happened is sort of ill-defined, and it just says, well, some of the, in some worlds, in one branch of the wave function, we say, that's the language, we got a 0, and in another branch of the wave function, we got a 1. There was no collapse. We're just asking questions to the thing that is part of the wave function in a way that we're not quite used to doing with the standard quantum mechanics. So I guess the measurement problem has now become being entangled with a system sure feels funny. And guess what? I'm a physicist. My sister is a psychologist. It's her job to explain why people feel the way they feel. Okay? My job is to explain how the universe evolves, and it's according to the Schrodinger equation.
All right. Well, we're not sitting here lightly. The gloves have come off. And for his own take on QBism, please join me in welcoming Professor Chris Fuchs.
Don't start. Don't start. Don't. I need a cable. Yeah. Used to be IBM.
Yeah, it's only 8 minutes in this branch.
These guys have given you so much nonsense. Who is this? QBism, the more careful way to explore reality. That's Pablo Picasso with his pistol. QBism takes its start in the, takes its start in the age-old debate that comes from 1925 when quantum mechanics was first discovered. The world is made of some stuff. But when physicists want to talk about the stuff, they introduce this symbol, a quantum state. And the age-old debate is about what is the relation between the stuff that's of the world and this symbol that physicists use for making calculations. One point of view that came up very early on was that the symbol represents a property of the stuff. So for instance, this thing that I'm holding in my hand has a certain rest mass. That is a property of it. Has nothing whatsoever to do with me. The alternate point of view is that a quantum state represents something like knowledge or information. It's not directly a property of the stuff, but rather what you know about the stuff or what you can predict about the stuff. QBism takes that as its starting point, that that's on the right track. And the reason it did is because things like our chairman here was talking about when he said, you make a measurement here and something far away is affected. That only is true if a quantum state is a property. If you drop the idea that a quantum state is a property, instead of it, think of knowledge, then you say, oh, what happened when I performed a measurement here is I learned something about what's going on over there. And it's not, well, because there's no color in the box. I can walk over to the box and open it up. And this is what my prediction is about. What I'm going to see if I walk to the box and open it up. Okay, so I say QBism is the careful way to explore reality. We take the idea that a quantum state is knowledge as the starting point, and then we try to refine that notion over the years. And the starting point really of the analysis is, what do we do with quantum states? Well, we calculate probabilities for measurement outcomes from quantum states. If we're going to say that, then we had better take the idea of, well, we'd better take it seriously. We calculate probabilities. But a question arises, what is a probability? What do we mean by a probability distribution? So around, when was this? Early 2000s, we took this point of view that the best way to understand probabilities is from the Bayesian notion of probability. You can see I was much younger then. I didn't have a beard. In the Bayesian approach to probability theory, probabilities quantify a degree of belief for a single trial without any a priori connection to limiting frequencies. So we played with this idea to see if it could give some clarity, bring some clarity to the quantum foundational debate. And it did bring. It had immediate explanatory powers. There's things that you learn about in your quantum information course, like the no-cloning theorem and quantum teleportation. And you could see that these effects arise just from the idea that probabilities in quantum theory are Bayesian probabilities. But as things developed, we wanted to push that point of view further. You get probabilities from quantum states, but also if you know the probabilities of all possible measurements, you can derive the quantum state. So it looks like you could take a point of view where we get rid of this thing that Graeme liked to draw a lot and put himself in, this quantum state, and instead only talk about probabilities, and at the end of the day, get rid of quantum states. They don't exist. And if they don't exist, they can't cause trouble. So you would think that QBism stands for quantum Bayesianism. There's a Q and a B. But there was a bit of a problem with this. And the problem was that in making this point of view consistent and airtight, we had to go ever further, more radically in our notion of Bayesianism. There's a broad range of views of probability that are called Bayesian, and we ended up in the radical end of that spectrum, a view of Bruno De Finetti, who said at the beginning of his book, my thesis paradoxically and a little provocatively, but nonetheless genuinely is simply this: probability does not exist. Probability is not something in the world at all. Probability is not something, a probability assignment is not something that can be right or wrong, can be true or false. It's a degree of belief, it's your best guess, but it's not something that can be right or wrong because your best guess, if you quantify it, is about you, not about it. So QBism became lonely for a B. We couldn't call ourselves Bayesians because a lot of Bayesians were throwing tomatoes at us because we had gone, we had become so right-wing or so liberal. I don't know which one you want to call it. So I started saying that QBism was like KFC. It used to be Kentucky Fried Chicken. Now it is just KFC. And Jilla, wherever Jilla is, it used to be the Joint Laboratory for Joint Institute. Yeah, it used to be that, but now it's just Jilla. Well, QBism was just QBism. But I ran across a letter from one of the old Supreme Court justices, Oliver Wendell Holmes Jr., to a friend. Believe it or not, the friend was named Einstein, but it wasn't the Einstein we all know. He wrote, Chauncey Wright, a nearly forgotten philosopher of real merit, taught me when young that I must not say necessary about the universe, that we don't know whether anything is necessary or not. So I describe myself as a betabilitarian. I believe that we can bet on the behavior of the universe in its contact with us. This is an important thing. We can bet on the universe's contact with us. We can't necessarily bet on what the universe just is, but what happens, what difference it makes to us. Okay, so here's QBism in a diagram. QBism in a diagram is there is this thing, we used to call it observer, let us call it an agent. The agent can take actions on a quantum system. It can push on them. For instance, it can throw them into Stern-Gerlach devices. And here I draw the equipment, the experimental equipment, as the hands of the agent. When the agent takes an action on a system, it leads to a new experience for the agent. These quantum states are not things out in the world, but they are means by which to calculate probabilities. What can these systems be? They can be anything in the world, anything whatsoever. You're a quantum system. Do you feel it? And an action can be anything that you can do. So in QBism, an action literally is anything an agent can do. I have 2 slides left. I'm running out of time. An action is anything from running across the street at L'Etoile. I was there some years ago, and I was standing at the street, and there's a tunnel, to go to the Arc de Triomphe. And there was a lady at the edge of the street, and she said, I'm going to go for it. Boom, 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 boom. She went through the cars. Now, she made a decision. She took an action on that big system, and it had a consequence for her. Either she lived or she died. I went through the tunnel, and I got to the other side, and I found that she was still alive. So that was good. But she made a decision. She would have been well advised to use a little probability theory first, and that would have helped her make a better decision. But usually, when we cross the street, we don't need to use probability theory. In this case, it would have helped her. For really refined interactions with the world, it is in our best interest to use probability theory, but go even further and use the apparatus of quantum theory. So another piece of QBism is that quantum theory is about making decisions and making the most refined decisions that you can. In our picture, the lab equipment is part of the agent. It's their way of acting on the world. Let me just end by saying this point of view is not popular with philosophers of physics because, well, their usual retort is, wah, wah, wah. You don't believe wave functions are real and you can't do that. Well, we do that. So let us quote Niels Bohr to end it. I felt that philosophers were very odd people who really were lost because they have not the instinct that it is important to learn something and that we must be prepared really to learn something of very great importance. Well, it's not only the philosophers. Bohr met Everett. Everett was a young student when he wrote his PhD thesis and had this idea that Graeme explained so beautifully to us. John Wheeler sent Everett to Copenhagen to meet Niels Bohr. And basically, Bohr said, this is bullshit. Thank you.
All right. Well, clearly the gloves are off. We have a whole series of questions, but we do want you to be thinking about your own. And again, in a few minutes, we're going to have you turn to your near neighbors and chat with them just for 2 or 3 minutes to come up with questions for our illustrious philosophers. Oh, sorry, theorists. I was just in the machine shop today. Do you have all 10 fingers, sir? All right. And so what we're going to have you do is each one of you is going to respond to the other in 90 seconds or less. You didn't tell us that. I have not told you that. I'm telling you that now, sir. You would have done well to examine the probabilities of what was going to happen next. So first off, I will say to you is, how do you respond to your colleague? Dr. Smith.
Well, there was a lot of talk about agents and beliefs and observers in Chris's presentation. Yeah. And to me, I prefer not to be in a situation where I'm asking what is an observer and trying to think about how people behave and act. I think the world can be described in a way that's much simpler than that and doesn't make a clear distinction between me and a pile of atoms.
I really don't make a distinction between you and a pile of atoms. And I don't make a distinction between me and a pile of atoms. It's just a different point of view. So the way I would say the Everettian view, or the presupposition of the Everettian view, or many worlds, what do you want me to call it?
It's typically known as the Church of the Larger Hilbert Space.
Right, and you're the deacon. In the Church of the Larger Hilbert Space view, the purpose of a fundamental physical theory is to be a kind of map of what reality is. The opposing preconception, the one that I was espousing or spouting out, was that science is an instrument. The world is far more unruly and lawless than our theories, I would say, in reality. The world is far more unruly and lawless than our best theories, give. The world is something, and we are swimming in this world, trying our best to not drown. And in this point of view, something like quantum theory is an instrument, is a tool that we can use to better survive. It depends upon the world. If the world were different, we wouldn't use a Schrodinger equation. We'd use the Smith equation or something. No, you like the Schrodinger equation. It starts with an S, too. Maybe you could co-opt it. Anyway, that's my response.
All right. Well, thank you very much. I've brought in a prop here, which is about as close to truth as we can get, I'm pretty sure. This is from our FET project, our internationally renowned project out of our department here. And I'm going to ask each of you in turn to help us describe. Here I've got a little gun. I've selected electrons, so clearly that's what's coming out of my little gun here. And I'm going to ask you at 3 stages what's happening here and there. Well, so 3 stages, sorry. 1 right there, right here, and right there. All right? Are you willing to do that? Yeah. All right, please. Dr. Smith.
Oops. So, go ahead, please. Yeah. Okay. So, there's something going to come out of that gun, and I can do a calculation that gives me some wave function describing the evolution of the thing that comes out of the gun. Of course, I can't look at the wave function, so this
it's right there.
Yeah. Okay. If you do the experiment, typically one will not constantly be tracking the path of the electron.
Correct.
Instead, one allows it to evolve unitarily. And then the electron has an interaction with a screen, and I have an interaction with a photon, and that's the point at which, if you take many worlds very, very seriously, you have to make sure you also describe my interaction with the screen and the photon unitarily. And we get the challenge of why does it look like the electron has landed in a particular location? And I answer the question, well, to another Graeme, it looks another way in another location. And he's asking himself the same thing.
Thank you very much. Dr. Fuchs.
Do I have to answer this one?
Yes. I mean, just in this world.
Yeah.
Sorry.
So I would say the facts on the ground is that the screen at the back end lights up somewhere.
Yes.
That's a fact. That's incontrovertible. Nobody can say otherwise.
That's a feeling.
That's a fact for one of you and an uncomfortable feeling for the other one of you.
And this picture that you're drawing is a picture of what? Is it of what's really happening? I'd say no, it's not. What it's describing is the evolution of my state of knowledge. My state of knowledge, or my state of belief, let's be true to ourselves here, is that I'll find a spark on the screen somewhere. I don't exactly know where, but the picture that we saw sort of evolving is just our method for calculating that probability of where it will land.
There you have it. One person is very comfortable, the other one not so comfortable. One person is grounded in reality, another person doesn't.
I said the facts on the ground.
All right. We do have many more questions, but more importantly, those questions should come from you. So what we're going to have you do is spend literally 90 seconds to 120 seconds, turn to your neighbor, and think about what ideas do you most agree with, what are ideas that you most wrestle with, and what questions do you want to ask? And we'll take as many questions as we can up until about a quarter till or 5:50. All right, folks. Thank you so much.
Hey, by the way, you spoke for nearly 10 minutes.
Did I?
Yes.
Whereof one cannot speak, therefore.
Clearly, we have some navigating to do. Clearly, we have some consensus to do and meaning making to do. And clearly, there has to be a winner and a loser. You all will get to determine
a second winner.
a winner and a second winner. That's very Boulder of you. Congratulations. There you go. Yeah, yes. Oh, it's only a winner if we measure it. Ooh. Actually, you know who the winners are. We're all the winners here for getting to here. Let's give a hand again to our luminaries. All right, so we'll take as many questions as we can, and I'm, for those of you of a certain age, going to run around like Phil Donahue and have you ask questions. So, first question right here. And if you don't mind, introduce yourself, please. You don't have to. Hi, I'm Noah, and...
Hi, I'm Alessandra. I'm an undergraduate student. I'm doing physics.
Perfect.
Okay. My question for Professor Chris Fuchs is, since you don't actually believe in probabilities, wouldn't that mean that your argument is kind of deterministic?
Di Finetti was trying to be dramatic by saying probabilities do not exist. So it's not that he doesn't believe in probabilities. His whole book was about probability theory. What he was trying to impress is that probability is not something that is out in the world. I use probability, and Professor Smith uses probability, and because they're not factive, they're not things that are true or false, it could be the case that he writes down a different probability distribution for something than I do. So it's not, that I don't believe in probability. And in fact, I do believe in indeterminism. I believe in indeterminism without objective probabilities. In other words, what the world is going to do tomorrow is not determined by what it has done today. New things will happen. There is new stuff in the world. There's new events in the world that can't be predicted by Laplace's demon. So those 2 points of view are not inconsistent.
Very nice. We're going to run over to the other side here. You can respond if you want to.
But Schrodinger's equation says that tomorrow can be predicted exactly by the state of the world today.
In the mind of God. You, in your branch, you I deified my opponent. In the mind of God. You wrote this big entangled state. Whose state of knowledge is that? If you take my point of view. Well, it's somebody outside of the universe. And if there's no one outside of the universe, then that thing isn't a real thing. That equation you wrote. By the way, I've got some general complaints about...
Yeah, so I'm wondering about I'm Heather Demarest. I'm a philosophy professor, actually philosophy physics. So I don't appreciate the shade. But
did you recognize everyone in...
I actually did. That was really fun. Yeah, that slide. And they were all giving their best glares, so those were fantastic shots. But yeah, I'm wondering about, in Everett, if you had an opinion about the probabilities. So I know this is kind of like a famous problem for the view, but you nicely gave us a 50-50 option, and it seems very plausible. Oh yeah, it divides into two, but you could have any probability you like. And so if you imagine a coin like kind of doubling every time you toss it, and one is guaranteed to land heads and the other tails, how could you ever get evidence that it was a biased coin or not? Because either way, you're going to expect exactly the same outcomes on all the different kind of branches, if you will.
And while you think about an answer to that, just so you know, Professor Demarest is an alumna from this very department.
Go see physics.
Well... I'm on. Okay. Well, first I want to say I got nervous last week, and I got some help with preparing for this lecture. I asked Twitter if anybody was aware of any plausible objections to the many worlds interpretation, and indeed many people showed up, and they most commonly talked about how do you derive the Born rule then. And the state of that is that it's not yet possible to do that effectively, but I think it is the biggest open challenge to this understanding. People try to do it. They say, well, probabilities are what fraction of the worlds do this versus that. And then, Zurich has this kind of, well, I guess I think it's fair to say none of them properly do that, and I think that is the biggest challenge. And if you're serious about many worlds in the Church of the Larger Hilbert space, you don't fully have to derive all the probabilities because they're pretend, right? Just like the measurements. And I still think it's important to make contact with others and try to derive the Born rule from some probably additional principle to just saying Schrodinger's equation. But we don't understand that yet. Can you derive the Born rule?
Actually, QBism takes the Born rule as its fundamental postulate. That's not a joke. It's in almost all of
Sorry, Dr. Fuchs, in layman's terms, could you explain the Born rule for our audience, please?
The Born rule is that thing which turns a quantum state into a probability. It's the mathematical rule that takes a quantum state as an input and a description of the measurement device as input, and then spits out probabilities. But if you play with the formalism enough, I don't want to say that. If you play with the formalism enough, you can actually rewrite the Born rule so that it doesn't take in a quantum state as an input and a measurement operator as an input, but rather it takes in a probability distribution as an input and a conditional probability as another input, and produces a third probability as an output. So when I say I'm taking Born's rule as an axiom, it's starting from that language and then trying to rediscover or rederive all of quantum theory from that as a fundamental assumption. And what I started to say, and I'll just say it quickly, of all the interpretive efforts, all of them but one always tries to derive the Born rule from something more fundamental that's not the Born rule. QBism turns that on its head and says the Born rule is the fundamental thing because it's about probabilities, and all the rest is kind of paper mache that's put in to build up the structure.
All right, thank you. We have another question over here, I think.
Yeah, so Graeme, I'm Josie Meyer. Graeme, you know me. Grad student in the physics education research group, so Noah would also know me from that. And this is a question.
Last night on the archive.
What?
There was a paper out last night. On the
Yeah.
Yours.
That's what we do.
Funny timing there, because that paper was actually accepted back in November, but I just put it on the archive due to some requests recently. So, anyway. So Graeme, I wanted to ask you about something that you probably aren't going to be super comfortable with, but I want to talk about morality here.
Morality.
And basically, so this is like one of the biggest qualms I have with many worlds. So basically, if you look at like my history, like we say that I'm here today, but there's some probabilities and some different decisions I could have made, different interactions I could have had with the environment if the environment was different, however you want to define that, that would have made me into a career criminal who's currently rotting in a prison cell. Now, so you say, okay, in this world we live in, Josie is in this room, and then some other one, she's in a prison cell. So the question becomes, why do I bother making any sort of moral choices? In other words, if all I'm doing by making moral choices is just making sure that this version of myself is not the one in the prison cell, who cares? Am I like trying to, is it really better to think about like the probability is actually Josie is here plus epsilon in a prison cell, and my goal is to try and reduce epsilon to as small a number as I can. But how does that fit into many worlds? This is something I've never understood, and I want your input on.
Okay.
Okay, now the gloves have come off.
Well, I mean, if we take the Schrödinger equation seriously, you're not trying to do anything right now. You're evolving. Briefly, it seems as though we're all here together in this world. Later, eventually, there will be no further evidence that we were here in this world, in this room. And indeed, asking whether we were in this room will have the same status as asking whether the electron went through one slit in the experiment or the other. There is no persistent reality of what's happening. We're just here for a while. It feels like we're here. Other people feel like they're other places. We have no basis for deciding that we're one of those people or the other. We just happen to be. And I can't offer an explanation for why we're in a particular branch, nor do I have any particular expertise or suggestions for how to live in a moral way. However, I do think Many Worlds offers us the opportunity to realize that we will make mistakes, but ultimately nothing is permanent, and those mistakes can be undone even if they appear to be irreversible, because everything is reversible according to a unitary evolution.
Let me just add to what Graeme just said. I love this. He himself showed us that the essence of the Schrödinger equation is that a vector in this vector space, this Hilbert space, just rotates. It just rotates. Now, in the many worlds interpretation, there is a universal state vector. Let's act like it's my arm. And the universal state vector, my arm represents the whole universe. And what is the whole universe doing? Well, it's just rotating like a clock. That's all the universe is doing. Now, one of our good friends, Ben Schumacher, the man who invented the word qubit, pointed out that if there is no further structure in quantum theory than the Schrödinger equation, where the universe is doing this, then there's nothing to stop us from getting in the rotating frame with the vector. And when we get in the rotating frame with the vector, that's what the universe is doing. The universe is doing nothing, literally nothing. And thank God you said this thing about morality.
All right, I now don't know whether I'm supposed to get out of bed in the morning or not.
No, but is it not extremely relaxing to realize that what is happening is nothing?
And our next question, please introduce yourself.
I'm Connor. I'm a PhD student in aerospace engineering.
We call that applied physics.
So do we. Typically, for a theory to be considered scientific, it has to be falsifiable. So I'm curious how you would falsify both of your theories.
Boom.
Watch this. Watch this. Falsifiability as a criterion for scientific theory has fallen out of favor. You're working with philosophy of science. The philosophy of science circa 1960. Popper's ideas are not current. From a pragmatic point of view, though, science is what scientists do. And what we are doing is groping for an understanding of a partial, a beautiful theory that we don't fully understand. And part of that is to discuss what it might mean and how it might be extended in different ways. And indeed, we're talking about how to interpret the theory. So not any differences between, I don't think any differences exist between us in terms of how we would use the theory and how we would predict experimental outcomes. However, we also try to think of the theory in the way that helps us most and helps us succeed in applying it to situations which we haven't used before, where we haven't used it before, and trying to push it to its breaking point. So in the case of many worlds, really to try to develop a consistent way to talk about measurement is, I guess, the impetus for or the reason for thinking about the interpretation of the theory. I know it doesn't answer your question, but it's definitely, I told you already, we did the experiment, we put Adam in a superposition, and he felt like it was definite outcomes, so.
Thank you for your question. It gives me an opportunity to say something that I've wanted to since I walked into this room. I know that many worlds interpretation cannot be falsified, because in fact the many worlds interpretation is just contentless. It is literally contentless, and I'm not exaggerating. Hugh Everett was a huge fan of science fiction, and he did his PhD work in the 50s. Already in the 1930s, you can find science fiction novels. There's at least two that I know of, where the